Here we go with lesson 2 of our introduction to vectors. I'll encourage even those of you who have taken physics to make sure that you're following along. You will find that there is some different vocabulary used in mathematics as opposed to physics that will be important to you going forward. One of the new terms you're going to hear today is resultant. This is the vector that results from the sum or addition of two or more vectors. And sometimes you'll just hear it referred to as the sum vector, but resultant vector is the most commonly used word. We've got two methods in which we can use to add vectors. So we first have the parallelogram law for adding two vectors. So the sum of two vectors A and B can be determined by completing the parallelogram formed by these two vectors when they're placed tail to tail. So you can see in our diagram here that these two vectors are placed tail to tail. So that's where the start of the arrows are. So they form some angle theta in between them. And if we, in this diagram on the right, you can see complete the parallelogram that would be formed there. So you've got BD, which is parallel to and the same length as AC. In other words, it's an equivalent vector. And CD is also an equivalent vector for vector B. Then we get this parallelogram, and the diagonal formed here, known as AD in this particular diagram, is where we see the resultant vector of A plus B. And you can see that because we know that this had a specific angle, well, that means this has an angle as well. So you can see here we're probably going to be using some trigonometry to do some of our solving. We can also use this triangle law of addition. This one will probably become more common because you can use it to add more than two vectors at a time. So the sum of our vectors is found by translating the tail of vector B. So the tail of vector B would be this guy here. And we're going to translate it over to the head of vector A. So that's what you can see here, right? It's been translated to the head of vector A. So it goes in the same direction, the same length as the previous B. And the resultants will literally go from the tail of A to the head of B. Okay, so here we have an example. So we're given two vectors, A and B. The angle between them is 60 degrees, and we know the magnitude of A is 3 and the magnitude of B is 4. We have to figure out what the magnitude of A plus B is going to be. So essentially what we know here, I know it's really hard to draw things with accurate angles and missing the lack of an actual ruler and a good pencil here, but I'm going to try my best. So I'm going to use this guy as vector B and this guy as A. And there they are, tail to tail. And it's supposed to be 60 degrees, so probably more like that. Try to draw diagrams in your notes and when you're doing questions as accurately as you can. You don't need to use a protractor to be super accurate, but make sure you're being really careful with at least acute versus obtuse angles because they can make a huge difference in your actual answers and what you see, especially when you get into doing word problems. But I also recommend that you do use a ruler and make sure your lengths of your vectors actually match up to what you want. So use some kind of scale and make sure that actually happens. Okay. So this was B, this was A. So you can see here the way I've set it up, it'll lend itself pretty easily to doing our parallelogram, but we can also change it up and set this up to do it as the triangle law. It doesn't actually matter which one, the math that will result from it will be the same. Okay, so here we have our triangle diagram. We got A plus B, where I've literally moved the tail of B to the head of the vector A. And we have our resultant vector A plus B. And because we know they form the angle 60 degrees, when we form the triangle, the obtuse angle here has to be 120 degrees. So that's this angle here. Has to be 120 degrees. Okay, so we have a triangle here with an enclosed angle between two known sides, which means we've set ourselves up to be able to use cosine law. So our resultant, and I'm also going to label our vertices here. Actually, just to be consistent with the previous one, we'll call it AC. So the magnitude of AC squared will be the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B times the cosine of the angle. So we know that A is 3, so 3 squared is 9. 4 squared is 16 minus 2 times 3 times 4. And the cosine of 120 degrees is negative half. So this will be 25 plus 12, which is 37. So that means the magnitude of our resultant is the square root of 37, which can't be reduced any. So if we're going to use a mathematical answer, that would be our final answer there. The magnitude of A plus B is square root 37. So one more definition you need is the zero vector. So just like there's a zero in terms of numbers, there is also a zero vector that literally does use the vector symbol. And literally it would result from the sum of two opposite vectors, just like the number 0 would result from the addition of two opposite numbers. So this allows us to think about what the difference of two vectors would be. Now remember that even with subtracting with numbers, for instance, 3 minus 2, well, that's the same as saying 3 plus negative 2. So that's exactly what we're going to do with vectors. The difference between two vectors is found by adding the opposite vector. So A minus B is equal to A plus negative B. So you can see from my diagram there, I've given you a vector A and a vector B, and we've also drawn the opposite vector B. So it has the same angle for the line, but goes in the opposite direction. So we would add both A and negative B together to find A minus B, and we would just use the same triangle or parallelogram methods from before. So here we have one more example. We're going to use it. It's going to help us to see some addition and some subtraction, and also be a reminder of things like equivalent and opposite vectors. So we have a vector A, B, and C that have been defined on this rectangular prism, and we're going to use them to express some other vectors. So you might take a moment to notice where some of those equivalent vectors lie, or how you might label some opposite vectors. So for BC, so we know that we're going from here to here. We can notice that that's actually parallel and the same length as vector A, but it does actually go in the opposite direction. So that means that BC is, sorry, my hand keeps drawing on it, is equivalent to negative A. So GF. So starting at G, ending at F. And we can notice that that, in fact, is also an equivalent vector, but this time not opposite. So this one will just be equal to the vector A. From O to B, so here's O, here's B. So this time we don't have a direct path already on the diagram, so essentially we have to form one. And you should be able to see that if we start at O, we can follow the vector B and then follow along CB to get to our result. So, and we know that this vector here is equivalent to A. So our result will be B plus A. Now, AC. So we're starting here this time, and we want to end up over here. So to do that, it looks like I have to travel backwards along vector A and then add B to it. So we're going to use negative A plus B in this case. And BG. So starting at B, and we want to end up at G on the back here. So of course, with many of these, there's two ways to get to what you actually want. So we can go up along BF and then backwards along FG, or we can go backwards along BC and then up CG. Either of those will work. And technically there's lots of other roundabout routes, right? Like we could do this and this and this and up to G. So you could actually add 4 vectors together, but once you simplify it, you'd see that you'd come to the same result if we take the more direct route along here. So let's actually go this way. We're going to go from B to F to G to get BG. So this vector here follows vector C, which is one we haven't used yet. Okay, so C. And then to get from F to G, that would be subtracting A. Okay, last but not least, we're going to go from O all the way to F. So you can see that's actually going to require us to do 3 vectors. And again, there would be multiple paths to get there. This could actually help you to see that addition is also commutative. So if we go back to this guy here, OB, we did B plus A. But we could also have done A plus B. It would be the exact same resultant vector. So this can be expressed both ways. Okay, so for this last guy from O to F, let's use C, and then we're going to go along DG, so that's adding an equivalent to B, and then along GF, which is an equivalent to A. So we're adding 3 vectors this time to get our resultant that we want.